Hello there, and thank you for joining me today. Today our topic of conversation are limits and asymptotes. And our objectives are to connect infinite limits with vertical asymptotes and connect limits at infinity with horizontal asymptotes. Now, you may have heard about asymptotes in previous contexts, put more casually, such as boundaries, force fields, imaginary lines that the function won't cross or touch. And those are great working definitions for some of our earlier math classes. But here from a calculus perspective, now that we understand the concept of a limit, we are able to more formally talk about these things called asymptotes. So, we have two halves to our time together today. The first is dedicated to these vertical asymptotes, right? And there's an example of one on the screen there. You can see it in the picture. A calculus definition of a vertical asymptote is if f of x approaches infinity or negative infinity as x approaches c from the left or right, then that line x equals c is a vertical asymptote of the graph of f. Consider the graph of f shown below. Practicing our limit notation here, if we discuss the limit of this function as x approaches 2 from the left, well, approaching 2 from the left, this graph is shooting down to negative infinity here. So this limit is equal to negative infinity. And if we analyze the behavior of this function as x approaches 2 from the right, well, from the right, this graph is shooting up to positive infinity. So from both sides of 2, we get that behavior, which makes x equals 2 a vertical asymptote of this function f. Now, finding them from a graph like this, not too terrible. We can literally see it in front of us and analyze that behavior. But suppose that we need to do some analysis without a graph. So what we might consider doing then is doing some analysis just by plugging in values, making a table basically. So here we have two functions f of x, very similar to each other. Okay, each one of these has a vertical asymptote at x equals 3. We've been asked to determine whether these functions approach positive infinity or negative infinity as x approaches 3 from the left and from the right. Okay, so to do this analysis here, we're just going to plug in some values, right? So we take a calculator, some type of technology, okay, plug in 2.9, 2.99. Of course, if we plug in 3, that's going to give us something undefined. So we can fill that into our table here, both of these tables. 3.01, 3.1, okay, just to get an idea of how this function is behaving on the left side of that vertical asymptote and on the right side. So to save a little bit of time, I'm not going to show those calculations, but I am going to fill in the table. Okay, so if we plug 2.9 into this top function f, we'll get negative 10, plug in 2.99, negative 100. Okay, now on the right side of 3, plug in 3.01, positive 100, plug in 3 1/10, we get 10. Well, let's now answer this question using our one-sided limit notation, the limit of this function as x approaches. And let's approach 3 from the left first. So we're looking at this side of the table, right? Coming closer to 3 from the left-hand side, numbers less than 3, like 2.9 and 2.99. Well, you can see that we go from negative 10 to negative 100, right? So it wouldn't appear even then that we're approaching a specific value. But I hope it's not too much of a stretch for you to think that if we had plugged in 2.999, now all of a sudden we would be at an even larger negative number, right? And so these values are headed towards negative infinity on the left-hand side of that vertical asymptote at 3. I'll compare that to what's happening on the right side of 3. Well, there we go from 10 to 100, and you can imagine what's going to happen if we get even closer to 3. Okay, we're going to get an even larger number. In other words, these y values are headed up towards positive infinity. Let's do the same thing for the example down below there. F of x equals negative 1 over x minus 3. Okay, and again here, I hope it's not too much of a stretch for you to understand that we're going to get these same y values, but they're going to be kind of flipped here, that negative causing a reflection across the x-axis, of course. Okay, so our behaviors are going to flip-flop here as well. This time, the behavior of this function to the left of 3, well, positive 10, positive 100, larger and larger positive values as we approach that vertical asymptote from the left. our values are headed up towards positive infinity, and as we approach that vertical asymptote from the right this time, negative 10, negative 100, larger and larger negative values, our function is headed towards negative infinity. So one way that we could do some numerical analysis to identify or confirm the existence of vertical asymptotes would be to make a table like this and see how those y values are behaving on either side of a supposed asymptote. Now, suppose we want to be a little bit more efficient with this. We don't want to make a table, we don't want to make a graph, or perhaps we don't have access to graphing technology. Okay, we can still find vertical asymptotes. And in particular here, we're going to focus on finding vertical asymptotes of rational functions. Okay, vertical asymptotes aren't random. They don't just show up randomly. They occur when there's an issue with the domain, when there's an interruption in the domain of that function. Right? And of course the domain being all of the numbers that we can plug in for the input variable without breaking any rules, such as having 0 in the denominator, which is what we have to worry about with rational functions here. So for example, consider f of x equals 6 plus 5 over x squared. We could, of course, graph that function and take a look, but even without the graph, if we can identify any interruptions in the domain, we could identify any possible vertical asymptotes. So looking at this function here, we've got an x squared in the denominator, and of course we can't have 0 as the ultimate denominator. Well, if we can't let x squared be 0, then in this case, x itself can't be 0, right? And there's nothing else happening in the numerator there. If we did plug in 0, we would get 5 over 0, which indicates to me, getting a non-zero number over 0, that indicates to me that we will in fact have a vertical asymptote at x equals 0. Let's go over to the right. K of n equals n minus 2 over n squared plus 4. Okay, focusing on the denominator there. Can't be factored at all, so that's not going to help me. If I set n squared plus 4 equal to 0 and solve, I would actually get complex solutions with the imaginary number I in them. So I'm not finding any real numbers that would give us a 0 in the denominator there, and so there's no vertical asymptote for this function. None. No interruptions in the domain there. Moving on to g of t in the bottom left. Negative 8 over t squared minus 16. Okay, here, again, looking for interruptions in the domain, looking for t values that would turn our denominator into 0. Factoring can be helpful here. It's not the only way to approach it, but it is a way to approach it. Here I can then see that there are two values that we would have to restrict. Two values that would give a 0 in the denominator, those values being negative 4 and positive 4. Okay. Now again, with just a constant on the top, negative 8, even if I did plug in 4 or negative 4, I would get negative 8 over 0, a non-zero number over 0. And that behavior there indicates to me that we do in fact have vertical asymptotes at negative 4 and positive 4. And we could of course confirm that graphically. In the bottom right now, h of y. I think a little factoring could be helpful here as well. Our numerator will be y plus 4, y plus 6. Denominator, y plus 3, y plus 6. Now I see two restrictions that we would have to put into place here. Right? Two values that would give a 0 in the denominator. So theoretically two potential vertical asymptotes. But now this is where we got to be careful. Okay? If we plugged in negative 3, we would get 0 in the denominator, and we would get some other non-zero number in the numerator. I can tell it's not going to be 0 because I don't have y plus 3 as either of these factors, right? So we're going to get a non-zero number on the top, we're going to get 0 on the bottom. That indicates to me that we do have a vertical asymptote. I guess I shouldn't have used y for our variable here, it's kind of strange, because this is a vertical asymptote with a y in front of it, but whatever, y equaling negative 3. Okay, but consider negative 6. If we plugged in negative 6 to this function, we would get a 0 on the bottom from this factor and 0 on the top due to this factor, right? And getting 0 over 0 is a different type of behavior, and that indicates a different type of discontinuity here. It's a removable discontinuity, which would show up just as an infinitely small hole at that point in the graph. Another way to think about that is the fact that these factors will cancel out. They will remove themselves, making this a removable discontinuity, not a non-removable discontinuity such as a vertical asymptote. So the only vertical asymptote we have here is at -3. We have another point of discontinuity, but it doesn't show up as a full-on vertical asymptote. And that could be confirmed graphically if you wanted to take the time to do so. So at this point, we have discussed vertical asymptotes at length, talking about their definition and how to identify them. Let's switch gears now and discuss horizontal asymptotes. In previous math classes, you had maybe talked about horizontal asymptotes as lines that the function approaches, or that lines they won't cross, like a floor or a ceiling or something like that. But now that we have this calculus background with limits, we can give a more formal definition. So a line, y equals b, is a horizontal asymptote of a function f of x if either the limit of f of x as x approaches positive infinity equals b, or the limit of f of x as x approaches negative infinity equals b. Put more casually, if the function goes way out to the right and approaches a specific value, or way out to the left and approaches a specific value, then that value is a horizontal asymptote of that function. Okay, the graph here shows two such examples. The limit of this function as x approaches negative infinity appears to be positive 2, if you trace this graph out that way. So y equals 2 is a horizontal asymptote for that reason. The limit of this function as x approaches positive infinity, as we go way out to the right, appears to be -3, and so -3, y equals -3, is also a horizontal asymptote of this function. Identifying horizontal asymptotes from graphs, just like vertical asymptotes, I mean, you can see them. They're not too challenging to find from that perspective. But what is more challenging is finding them without a graph. Okay, now here again, we're also going to focus first on just rational functions, because there's some nice little shortcuts we can use to identify horizontal asymptotes for rational functions. So like it says here, to find the horizontal asymptote of a rational function, we compare the degree of the numerator with the degree of the denominator. That is, compare the largest exponent in the numerator with the largest exponent in the denominator. And there's three things that could happen. Okay. Scenario number 1. The degree of the numerator is smaller than the degree of the denominator. In other words, bigger exponent in the bottom. Well, if that's the case, like this top says here, then we're going to have a horizontal asymptote on the x-axis, that is y equals 0. Okay, and on the next slide, we'll talk about why that behavior would manifest in that horizontal asymptote. Situation number 2. If the degree and the top and bottom are exactly the same, then the horizontal asymptote can be found just by identifying the coefficients of the highest degree terms, a over b. That's the middle scenario here. Finally, the third situation, if the degree in the top is larger than the degree in the bottom, then there is no horizontal asymptote. There's a different kind, which we're not going to focus on here, but there is no horizontal asymptote. So that's a quick summary of the kind of the rules or shortcuts for finding horizontal asymptotes for rational functions. Here we'll try to explain a little bit about, why those rules kind of work. Okay, so starting at the top, we've got this rational function g of x made up of a quartic trinomial on the top and a quartic polynomial in the denominator. Remember, the textbook definition for a horizontal asymptote involves limits at infinity, right? At very large, either positive or negative x values. So one way that we can kind of think about it is this way. If we're plugging in 10, 100, 1,000, 100,000, 1 million, we're plugging in larger and larger and larger x values. Really, 9 and 12 don't contribute much to that conversation if we're plugging in very, very, very extremely large x values, right? Even a regular x is like a kind of a drop in the ocean at that point. Okay, and the same could be said about these terms. It's really these two terms that are kind of determining the behavior of this function for extremely large x values. So really we can ignore everything else except for those highest degree terms, 6x to the fourth over 4x to the fourth. So really we could identify any horizontal asymptotes by considering the limit of this function as x approaches positive infinity, and really just looking at those highest degree terms. Well, a little bit of canceling here, and I'm, being somewhat casual about this, but trying to get to the point here. those x to the fourth really kind of cancel out, and we're left with a constant 6 over 4, which reduces down to 3 halves. So this graph will have a horizontal asymptote, y equals 3 halves. Okay, that's that scenario where the degree in the top and the bottom are the same, and because we can ignore all of those lesser degree terms, when we compare them, those degrees being the same, they cancel out, and we're left with just those coefficients, a over b, like we saw on the previous slide. Moving on to s of t. Here now, in order to use our kind of shortcuts and our rules from the previous slide, we're going to want to actually multiply this out. Okay, but really all I care about are the highest degree terms in the numerator and the denominator, right? So I can FOIL everything, or I can just recognize that the highest degree term I'll have in the numerator is a negative t squared, and the highest degree term I'll have in the denominator is a positive 3t squared. And remember, all of the lesser degree terms, they'd really have no bearing on this function's behavior for extremely large x values. So I can focus just on the negative t squared over the 3t squared. And like we saw up above, if we consider the limit of that as x approaches infinity, these t squareds really cancel out, and we're left with a negative 1 over 3. So this function will have a horizontal asymptote, y equals negative 1/3. Picking up the pace a little bit now, moving on to h of t, I'm comparing the highest degree terms. Notice here that we've got a t cubed in the bottom and only a t squared on the top, and that indicates that we have a horizontal asymptote along the x-axis, y equals 0. Okay? To try to think about why that is, because the degree in the bottom is larger, the bottom is going to grow faster than the top. And if you've got a fraction where the denominator is growing faster than the numerator, the value of that fraction is getting smaller and smaller and smaller. You're going from 1/10 to 2/100 to 3/1000 to 4/10,000. Those values, if you compare them as decimals, are getting smaller and smaller and smaller. In other words, they are approaching 0. Horizontal asymptote, y equals 0, when the degree in the denominator is larger. Compare that to f of a at the bottom here, where the degree in the numerator is larger. Okay, here there is no horizontal asymptote. In this case, the top is growing faster. And in a fraction, if the numerator grows faster, then this value is going to grow without bound. There's no bound to this for larger and larger a values. So that's how we can use kind of some shortcuts to find horizontal asymptotes of rational functions quite quickly without having to consult a graph. Okay, so then you might ask the question, what do we do with other types of functions then? Trig functions, exponential functions, how do we find potential horizontal asymptotes there? Well, in that case, we've got to slow down, do a little bit more analysis, and rely on our understanding of what those functions behave like. So consider f of x equals cosine of 4x over x. Remember, the definition of a horizontal asymptote requires us to think about this as a limit as x approaches positive infinity or negative infinity. So let's consider for a moment the limit of this function as x approaches positive infinity. That is the limit of cosine 4x over x as x approaches positive infinity. Well, I'm going to be a little bit informal with how I write this stuff down, but I think that's okay. Let's think about how the bottom of this behaves. Let's think about just how x behaves as x approaches infinity. Let's not overcomplicate it. X is going to keep growing and growing. You plug in larger and larger x values, x is going to get bigger and bigger. The denominator of this is going to get bigger and bigger and bigger. It's going to head towards infinity. Think about the numerator though, cosine of 4x. That's our cosine function with a horizontal shrink by a factor of 4, right? Well, understanding a little bit about how sine and cosine behave, they oscillate back and forth between positive 1 and negative 1. Their y values do. So even if you plug in larger and larger x values, you're going to continue to get that periodic oscillating behavior, bouncing back and forth between negative 1 and positive 1. So as x approaches infinity, the denominator of this function grows without bound. The numerator, though, is stuck between negative 1 and positive 1. So like we talked about previously, if the denominator is growing that much more quickly than the numerator is, then this function will eventually start approaching 0. We're going to have a horizontal asymptote, y equals 0. Now, if we consider, that was positive infinity, right? Consider the limit of this function as x approaches negative infinity. Well, the same can be said about the numerator, right? That oscillating behavior, whether you're plugging in negative values or not. So I'm just going to do these symbols because it's the same. Okay, now x, if you make x approach negative infinity, well then x literally will head towards negative infinity. Okay, and even though it's a negative number there, the value of these fractions will again get smaller and smaller and smaller, approaching 0. And so even if we analyze out to the left end behavior there, we still got the same horizontal asymptote, y equals 0. Let's finish this now by talking about one more function here, this one involving an exponential piece, h of x equaling 4 plus x squared over 3 plus e to the power of x. Okay, let's first think about this, and let's first understand something we already kind of talked about. For large x values, adding 4 and adding 3 is really not changing the behavior at all, and so we can really kind of jump to ignoring those right away. But let's consider the limit of this function as x approaches positive infinity first. That is x squared over e to the power of x. Again, we can ignore the adding 4 and the adding 3 for large x values. Okay. You know, x squared is going to grow without bound, right? And so will e to the power of x, but these two functions are kind of not on the same playing field in regards to how quickly they grow. Right? A quadratic function grows relatively quickly, but e to the power of that x value is going to grow even faster. Exponentially is the phrase that we would use there, right? So because this denominator will grow faster, and it doesn't matter that it's e to the power of x, it could be 2 to the power of x, 4 to the power of x, something like that. Here we have a denominator that's growing more quickly than the numerator, so like we've discussed, the value of this fraction will get smaller and smaller and smaller as you plug in larger and larger and larger x values, and that means that we are headed again here towards 0. We've got a horizontal asymptote, y equals 0. Let's consider, though, the behavior as we head to negative infinity. Okay, well, x squared is going to behave the same way as it did when we were approaching positive infinity. We're squaring those values, going to get the same type of behavior. But let's think about plugging in negative numbers for that exponent for e there, right? I'm getting kind of informal, kind of casual with how I'm writing this down, okay? But, you know, if we plug in really large values, if we plug in negative infinity, which, again, being a little bit informal here, this is what I could write down at least to get something going here. Well, if we square really large negative numbers, they're going to be really large positive numbers. But think about what happens if we plug in a negative exponent. If we have a negative exponent down here on the bottom, say negative 100, remember what a negative exponent tells us to do. It tells us to take that term and take its reciprocal. Or casually put, it tells us to flip it to the numerator. So for large negative x values here, this term really is going to end up being multiplied to these really large positive values in the numerator. So really we're going to have really large positive values multiplied by really large positive values, and so we're going to get really large positive values. So we do not see the same type of behavior as x approaches negative infinity here. We still have a horizontal asymptote from that right end behavior, but we do not get one from the left end behavior for the reasons that we just discussed. So be careful with those exponential functions in regards to finding horizontal asymptotes, especially with your negative infinity analysis there. Remember what a negative exponent is really having us do. So, thank you for sticking with me here as we discussed asymptotes and how we can connect them to calculus using the concept of limits. Thank you for watching.